Welcome to part 2 of our microtheory math review. So in our last, part 1, we covered a lot of math basics. And the goal here in part 2 is essentially to start with the idea of slope, the basic idea of slope, and to move slowly all the way through to the idea of derivative, okay, or the derivative. So we're going to start out with slope. That leads us to talking about tangent lines. And then to really be able to put together the derivative, we need to introduce the idea of limits. So that's essentially what we're going to do in this video here. So we're going to start with the simple idea of slope, work all the way up through to the idea of the derivative. Because again, remember, the derivative is just simply the slope. That's all it is, right? So we're going to start with what we know of the slope from Algebra 1 and work all the way through to calculus, okay? So I know those of you who maybe don't love math as much as I do, the derivative can sometimes seem weird or difficult, but it's important to keep in mind that all the derivative is the slope, right? It's just a way to find the slope in a lot of different situations, okay? So don't be intimidated by the idea of the derivative. It's actually a pretty simple basic concept. So that's what we're working on. That's what we're working up to in this video. All right, so last time we spent a lot of time finding the slope of lines, whether it's with a function or whether we had 2 points and so forth, right? But what we're going to be working on here is finding the slope of a nonlinear function, okay? And what we mean with that is really, what is the slope of a line at a particular point of that function? Okay, because obviously if you have a circle, the slope as you move around the circle is going to change all the time. And so what we're really talking about here when we talk about the slope of a nonlinear function, right, the slope of something other than a line, what we really mean is the slope of a function at a particular point, right, that is tangent to that particular point. That's essentially what we're talking about. We're talking about the slope of a tangent line to any sort of curve. That's what we're getting at. So many of you may be thinking, sure, tangent lines. Some of you may be thinking, tangent line? So what's a tangent line? It's a pretty simple idea. All it is it's basically a line that just touches a graph at one point and one point only, right? It's infinitesimally close touching the line, okay? So in reality, for kind of in math speak, a tangent line happens to be exactly perpendicular to the function at that point. And we'll look at some graphs on the next slide. This is what in mathematics we would call orthogonal. The idea of things being orthogonal is actually really important in wireless communications and all kinds of cell phone communication. So it's a really important concept, but we don't need to dive into that complexity here. All we really mean is the tangent line happens to be exactly perpendicular or orthogonal to a particular graph. Okay, that's it. So let's take a look at what we're talking about, right? So which lines are tangent? That is, which lines just barely touch a nonlinear function? Well, we've got 2 sides here. This is our circle. Okay, and obviously this line here is tangent. Okay, that is, it just barely touches the circle at one point right there. Okay, again, I've drawn these with large lines, so yes, it looks like it's touching in a bunch of places, but that's the tangent point there, right? This happens to go right through the middle of the circle, so it is not, go in black, right? This is not a tangent line. This is not a tangent line as well because it intersects the circle at 2 points, right? It can only just barely touch it at one point, okay? Now on the right-hand side here, where we've got our old trusty parabola from part 1, right? This purple line here is tangent because it is just barely touching the parabola right there, okay? Roughly right there. Right, so this line is a tangent line as well, tangent. So that's what we're talking about here. We're saying, okay, let's see if we can find the slope, whoops, come back, the slope of a line that is just tangent at that point. That's all we're trying to do here as we build up towards the derivative, okay? All right, so that's what a tangent line is. Now, to start with, we got to go back and start with what we know, and that is the slope between 2 points on any graph of a function. Okay, I'm going to start off with a parabola, y equals x squared, just because it's nice and simple. Okay, so let's go back to the way we thought about this. That is, right, the slope, m, is equal to delta y over delta x, right? Rise over run. And remember, this was y2 minus y1 over x2 minus x1, okay? So, the slope of this line here that's going through points P and point Q, right? Well, let's solve it. So m is equal to y2 minus y1 divided by x2 minus x1. So y2 is right here, 9, okay, minus y1, geez, PowerPoint, is right here, 4, divided by, well, x2 is right here, the number 3, minus x1, which is 2. Ay, ay, ay. Okay, let's get the eraser here. I should have put, there we go. Let's fix that. This is 3, and x1 is 2. So we put 2 in there, okay? So 9 minus 4 is 5. 3 minus 2 is 1. The slope here is equal to 1, okay? All right. So that's what we did in our last lesson, and this basically tells us the slope of the line through these 2 points. Now, notice what I'm trying to do here is I'm trying to make a line. It's getting closer and closer to being tangent on this graph. But as we can see here, this line that I've drawn is not quite tangent, right? It intersects the line. It doesn't just touch it at one point, right? But it's kind of close to being tangent. So this approximation here is getting close to the slope of this function at P, but it's not exactly the same, okay? But it's a good start. Okay, so to kind of summarize, right, this is close to the slope of the function at P here, right? But this line is not tangent, it's close. But what we're going to do, essentially, for the rest of this video is really one thing. We got to build up to do it, but all we're going to try to do is say, okay, let's start with the slope of this line, and we're going to slowly move Q this way. We're going to bring Q closer and closer to P. We're going to move it down this way, and keep moving it this way, and as you can see, as we bring Q closer and closer to P, this line that goes through P and Q will become closer and closer to being tangent. So if we look on the next slide, right, if we go back and forth, see how that line slowly moves over that way until it's exactly tangent. That's essentially all we're going to be doing. That's the idea of what we're trying to do here with the derivative, okay? We're essentially going to move Q closer and closer to P until we get to the point where the slope of the function at P, right, is the slope of that line. Until we essentially have this. That's supposed to be an arrow. The slope of the tangent line. Okay? I'm going to work on my handwriting because I've just consumed large quantities of coffee. All right, so that's what we're working towards here. Okay? So, to kind of make the math work and to be understandable, we're going to have to introduce a little bit of an additional notation. Now, many of you have already seen this, but what we're going to do is we're going to start to use these terms delta x and delta y. Okay, that is, right, some sort of little bit of change in x and a little bit of change in y. Okay, so instead of having numbers for p and q, right? So remember before we had P was 2 comma 4 and Q was 3 comma 9, right? We're just going to use X and Y and delta X and delta Y, okay? So what that means is we're going to say, all right, the point P is somewhere. It's some point, and it has an X coordinate and a Y coordinate, okay? And then we're going to say, all right, there's this other point Q, right? And again, what we're eventually working towards is moving Q towards P. So we're going to say, look, Q is always in reference to P. So Q is just, you start with the X coordinate of P and you add a little bit. So X plus delta X is the X coordinate of Q, and Y plus delta Y is going to be the Y coordinate of Q, right? So this part here is kind of like our 3, and this part here is kind of like our 9, right? You would essentially have 2 plus 1 and 4 plus 5 on the right-hand side here, okay? So that's what we're going to do. We're going to switch to this notation just because it makes the general functional form a little bit easier to write, okay? All right. So now, coming back to our graph, what we're trying to do is find the slope at 2 points on the graph. And really, it's a graph of any function. So we can kind of think of this as, instead of y equals x squared, again, this is still a parabola, we'll just say, look, this is going to be any function f of x, okay? And now, instead of 2 and 4 here for p, we just have x and y. And instead of, PowerPoint, come on. And instead of 3 and 9 for q, we have x plus delta x and y plus delta y, right? All we've done is just kind of put them in x and y notation, okay? All right, so now let's work through what we're kind of working towards, and that is, let's find the general case of the slope through any 2 points on a curve, okay? So that is any function, right? We're going to start with some function f of x, right? It could be y equals x squared. It could be y equals x cubed. It could be y equals 2x plus 3. It can be whatever we want. Any function, just some function of x, okay? And we're going to start with our 2 points, P and Q. And P can be any point, and Q is any other point, but we put the coordinates as being in relation to P, okay? Because again, remember, we're going to take Q, and eventually we're going to move it closer and closer to P, okay? So that's what we're trying to do. Let me make sure, yes, okay. So before we jump over and start to kind of work through some of the math, let's, again, just talk about functional forms here, right? So we're going to start with some function. We have our 2 points P and Q, and we're kind of doing what we have done before, okay? Now, remember, when we think about some function, f of x, remember, this is just a function where we have an input, which is x, and an output, which is f of x. And remember, oftentimes we just call this y. But with a function, we have an input and an output, okay? So with this graph, right, this is just some function now. For p, we put in some value of x, and we get out some value of y. So y here is just f of x, okay? And the same thing is true up here. You put in some x value that happens to be a really long convoluted x plus delta x, and your output you get out here is this. And this is just f of x plus delta x, right? So again, I'm coming back to this idea, right, that y is just f of x, and for the second point here up here at q, y is just really f of x plus delta x, okay? So again, we've moved away from using 2 and 4 and 3 and 9, and we're just using x's and y's, okay? All right, So now let's jump to this, which will allow us to kind of work through it. Okay. All right. So we've got our function f of x, we've got p, and we've got q. All right. And what we're going to do is say, all right, we just talked about functional form, and we know for point q here, right, that the output part, y plus delta y, is just f of x plus delta x, right? We're just saying the output part, right, this part here, is found by taking the input part here and plugging it into our function f, right? So we put this stuff in here and we get out of our function this stuff here, okay? So we know y plus delta y is equal to f, the function f of x plus delta x, okay? So, like we always do with math, let's do some rearranging, okay? So we're going to rearrange this expression here, okay? We're going to rearrange and solve for delta y. So we don't have to do much in the way of rearranging. So we just bring y over to the right side. So we have delta y is equal to f of x plus delta x, right, minus y. All right? Okay. But from what we had just done, we know that y here is just simply f of x. Okay? So now, let's go ahead and sub that in. All right, so let's sub in, okay? So that means delta y is equal to f of x plus delta x minus f of x, okay? So now, essentially what we've done is we've got something in terms of y on the left-hand side and everything in terms of x on the right-hand side, okay? All right. So now, remember, right? So what we've just derived here is this. Delta y is equal to f of x plus delta x minus f of x, okay? All right. Now, if you think about this expression, it kind of makes sense, right? Basically, this is the, over on the left-hand side here, right? This is the y part of q, right? And if you subtract from it the y part of x, the y part of p, right, you're going to get delta y, okay? Now remember, what we're trying to do here is come up with an expression for any function that represents the slope between 2 points on that function, right? Basically the slope of any line through 2 points for any function, okay? All right, but we know, right? Let's start with the basic, right, slope, m, right? M we always use as represent slope, is equal to delta y over delta x, right? Rise over run, okay? Well, this actually up here looks, if I could do arrowheads, there we go, looks kind of similar. So why don't we divide that equation by delta x? We're just going to divide both sides of this up here by delta x, okay? So what we're going to do is divide by delta x, okay? So let's start with delta y is equal to f of x plus delta x minus f of x, right? So all we've done here is just brought this equation from above and brought it back down here, okay? So now we're going to divide by, and we're going to do this right here, divide by delta x. Okay, so divide both sides by delta x. That means we've got delta y over delta x is equal to f of x plus delta x minus f of x divided by delta x. Okay, and voila, right? What we have here is a general expression for the slope of a line through any 2 points on a curve, right? So slope equals this thing up here, right? This whole expression here is the slope, okay? So let's actually try it out. That's what we should have on the next slide. So we just derived this expression here. The slope is equal to this weird convoluted thing, f of x plus delta x minus f of x all over delta x. So let's see what the heck this means. So let's think back to that original function and idea we started with at the beginning of this beginning of this video, right? We found the slope between 2 points, P and Q, right? And recall that the slope was equal to 5. When we use the equation, m equals y2 minus y1 divided by x2 minus x1. All right? Well, this is an equation for slope. And let's see, right? It should match, okay? So we've got P and Q here. P, right, our x is 2, and our y is 4. And, okay, and, right? And so Q here is x plus delta x. Well, our delta x, come on, geez. Our delta x is right, can my Apple Pencil die now? I swear. Microsoft and Apple, you guys kill me. There we go. This is our delta x, and this is our delta y. Right? So remember, everything is in relation to P. So Q is now 2 plus 1, right? That's the x part. And the y part is 4 plus 5, okay? So let's see if this works. Let's try it out. All right. Again, that example we started out with was y equals x squared, okay? So m is f of x plus delta x minus f of x divided by delta x, okay? All right, so this should equal to, well, f, right? X plus delta x is 2 plus 1, or just 3, but I'm doing it in small steps, right? Minus f of x, so it's going to be the function of the, right? 2 right here is x, so of 2, okay? Divided by delta x. Well, what's delta x? Remember, that's the increment that we increase the x variable from. We go from P to Q. So we go from 2 to 3. Remember, delta x is right here. It's just 1. So delta x is just 1. Okay? Okay? Well, the function is y equals x squared. So this is just f of 3 minus f of 2. Well, if our function is y equals x squared, then this is equal to 3 squared minus 2 squared, which is equal to 9 minus 4 equals 5. And voila, right? We get the exact same answer as we got in the first example that we did, okay? So what we've derived now is a general expression that'll allow us to find the slope of a line through any 2 points on any function anywhere in the universe. Pretty cool. At least I think it is. Okay. All right. Now we're getting there. We're pretty close. Let's jump back to PowerPoint here. Okay. So we're getting close here, right? We're getting pretty close to having the derivative, right? And again, all we've really been concerned about is the slope of a line. Again, derivative, just the slope of a line. Okay. But now what we have is a general expression for the slope of a line through any 2 points of any function. Okay. And the last step, what we're going to do is now bring point Q, this is what we've been saying we do all along. We're going to slowly take Q and move it closer and closer to P until the line becomes a tangent line, and that's when, voila, we will have the derivative. Okay, so again, derivative is not some complex or mysterious thing. That's all it is a slope, and we're just working towards that. Okay, now, the one last step or piece of notation we need is this idea of moving closer and closer to something or approaching it. Okay, so when we talk about moving the point Q closer and closer to P, what we really mean is we're going to make this delta x smaller and smaller. Okay, that is, it's basically going to slowly become 0. Okay, now in math speak, in mathematics, we call this a limit. So this is the idea of a limit. So those of you who've seen this before know what a limit is. If you haven't seen it, it's nothing very complicated. It's the idea of, right, what does something or what does a function become if you kind of approach something forever? You do it forever, right? Or kind of in math speak, right, what does a function become if we slowly approach some value of x? Okay, so let's just kind of think about that. First way to think about it is a goofy example. Hopefully it's goofy. Hopefully none of you guys want this to happen. But let's think about, right, what happens to me, Dr. Connors, as time approaches infinity. Well, right, we are mortal beings. At some point we all die. So, not to be morbid, but just to kind of goof off, right? The way we would write this in mathematics is we would say the limit, and we write Lim, and it's always the script L, okay? And we write kind of the idea of the limit below it. So we would say time as it approaches positive infinity for Dr. Connors equals, well, I'm not going to live forever. At some point, I'm going to die. So we'd say equals dead. All right? That's a goofy example, obviously. But that's essentially the idea of limits. We're just saying what happens if you do something and you approach it kind of forever, right? Or what does a function become if you kind of slowly get closer to this value? Like, what does it become, okay? So let's get away from these morbid details and let's think more in terms of mathematics. Okay, so, right? Again, this is the way we write it. We write the limit, and then we say, okay, the limit as x does what, and we write that underneath it, okay? And so we're saying, okay, what happens in the limit as x approaches 0 for this function here, x squared? Well, as x becomes smaller and smaller and smaller, x squared also becomes smaller and smaller and smaller. So you can actually try it out over here, right? So think about this. Right? So let's say x is equal to 2. Well, we know x squared then is equal to 4, okay? All right, let's set x equal to 1. Well, x squared in that case is equal to 1, okay? Let's set x equal to 0.5. So we're getting smaller and smaller. Well, x squared of 0.5 is just equal to 0.25. Right? Again, as x gets smaller, right, x squared also gets smaller. So in a limit, if we kept doing this forever and ever and ever and ever, x squared is just going to equal the limit as x approaches 0 for x squared is going to be equal to 0. Okay. Now, many of you who have done limits realize, well, what you do is you just put this 0 in for x squared. 0 squared is just 0, okay? That's kind of what you do for a lot of limits, but you can't do it for all of them, right? Because sometimes functions are discontinuous, so you got to be careful about that. But that's essentially all you're doing, okay? So let's evaluate this one. As x gets closer and closer to 2, okay, what happens to this expression? Well, this expression is going to get closer and closer to 7, right? 3 times 2 plus 1 equals 7. So the limit as x approaches 2 for this function approaches 7, okay? Approaches, there we go, approaches 7, okay? All right, now we've got all the pieces. We've talked about this idea of limits, right? And we have everything we need to understand the idea of the derivative, okay? So the derivative is basically function that gives us the slope of a line that is tangent to a different function at some particular point, okay? So we're going to start with the general function that we've derived that gives us the slope of any line through points P and Q. And what we're going to do is use this last piece. We're now going to bring Q closer and closer to P until the line becomes tangent, okay? And when we bring Q closer and closer to P, we're going to be talking about the limit, and essentially we have all the pieces we need to talk about the derivative. Okay, so now going back to our graph, right? All we're doing now is moving Q this way, slowly bringing it along the curve, slowly bringing Q down here, until it gets closer and closer and closer and almost touches P. And in the limit, it essentially will, but it never actually does, okay? Okay, so we know this general expression, the slope here of any line through P and Q. That's what this expression is. But what we're going to do is say, all right, let's let Q get closer and closer to P, okay? That is what is this expression as delta x approaches 0. That's essentially what we're doing. Right? We're bringing Q towards P. We're bringing Q towards P, and what we're doing is we're going to say, all right, let's let this piece here get closer and closer to 0. Right? As this gets closer and closer to 0, then Q is getting closer and closer to P. Okay? So the slope then will be a limit as delta x approaches 0 of f of x plus delta x minus f of x all divided by delta x. Voila, that is the definition of the derivative, okay? And that's all we did. So all the derivative comes from is basically saying, okay, theoretically, I'm going to take this point Q and I'm going to move it this way till it gets closer and closer to P. And as it does that, this line here becomes closer and closer to being tangent. And in the limit, it is, and it is the derivative, okay? So that's it. This is the general expression for the derivative, okay? So this is saying the slope of tangent line, right? Because as Q approaches P in the limit, this part here says this line becomes tangent, okay? All right, this is the derivative now. The next video is where we'll actually go through and do some examples. But this video primarily kind of goes through and just shows you where it comes from. Okay. Now, oftentimes what you'll see, the notation that's often used is f prime of x. Okay. So that's what this means. F with a little apostrophe there and of x. This is f prime of x. Okay. So if you were to say that, that's what that means. F prime of x is equal to the limit as delta x approaches 0 of the expression f plus delta x minus f of x divided by delta x. Okay. Or you'll oftentimes see it written as du dx, where u represents just some function. Right? So if you're taking the derivative of some function, you'll see it written as this way. Now, a lot of times the way people use it is that they're usually having some function of y equals something f of x, and therefore you would just write it as dy dx. Okay. So the two most common ways you're probably going to see it is this way and this way. So dy dx and f prime of x. But all those, that just basically means the derivative. Okay. All right. Now, the nice thing is that everything here is a function of x. Okay. So as we work through some examples in the next part, right, all we'll need is essentially the rules to understand how to simplify our notation, but it's always as a function of x. Okay. All right, so that is essentially that is how we went from basic idea of a slope all the way through to the idea of a derivative. Now, some of you might be thinking, all right, what the heck does this give me? That's what we'll do in the third video, is just do some examples of using this, and you'll see it's actually quite simple, okay? Some of the math might get a little bit long as we work through it, but the idea is pretty simple, okay? All right. And so that is it. That is a wrap on part 2 of this part of the math review.